Alright, in this video we're going to introduce surface integrals of vector fields, which are known as flux integrals. And now we discussed flux across a curve in 2 dimensions, and so here we're going to look at flux across a surface in 3 dimensions. So let's suppose we have some fluid flowing across our surface S, and the vector field F here in yellow denotes the velocity of the fluid. So how can I go about computing the rate of flow of the fluid through the surface S? Well, let's first find the rate of flow across a small little patch of the surface. And the rate of flow across this patch is just the volume of fluid that passes through this patch per unit time. Okay, so how can we go about finding the volume then of the fluid? Well, given that the fluid is flowing in the direction of F, which forms the angle, say, theta here, with the normal direction to the surface, we can find the volume of this skewed box by multiplying the height of the box times the area of its base. Okay, so now how do we go about finding the height of the box? Well, for that, we want to find the projection of this yellow velocity vector onto the normal direction, right? The scalar projection of that vector onto the normal direction will just give us the height of the box. And if n is a unit vector, so in other words, I could take n to be this cross product vector, so tu cross tv, which just comes from the parameterization for the surface S, and divide it by its magnitude. That's going to give us a unit vector in the normal direction to the surface. And then if I just take the scalar projection of f onto that vector, that's going to give me the height of the box. Okay, now what's the area of the base of the box? Well, that's just ds, right? That's just going to be the differential surface area element. Okay, so putting that all together, okay, we're going to call the flux through ds to be the volume of fluid that flows per unit time through this little patch. And as I just said, okay, the height of the box is just the projection of the yellow velocity vector onto the normal direction. And that's just going to be f dot n, right? So if I look at this right triangle here, okay, then the height here is the adjacent side of this angle theta. So I want to take the magnitude of f, that's just the hypotenuse of that triangle, times the cosine of the angle theta. But see, if n is a unit vector, then its magnitude is 1. So this is really magnitude f, magnitude n, cosine theta. So that's just f dot n. So f dot n tells us the height of this box, and ds, as we just said, right, that's the differential surface area element. That's the area of the base of this box. So its product will give us the volume of fluid that's flowing across this little patch per unit time. Okay, so then to find the total flux across the surface, we're just going to add up all of these various rates as we let these patches vary over the surface, and then we're going to just integrate, in other words, right, because we're adding those rates up. So if we integrate this quantity here over S, that's going to give us the net rate of flow of the fluid through the surface S. All right, cool. So let's go ahead now and talk about how we can compute one of these things. Well, we've been talking about computing surface integrals in terms of the parameterization for the surface S. And we're going to do that same thing here. Now note that this quantity f dot n ds simplifies quite a bit actually because of the following fact, right? N is tu cross tv divided by the magnitude, and ds, as we've derived, is the magnitude of that cross product vector times dA. And see, very nicely, the magnitudes here drop out, and we just wind up with f dot that cross product vector dA. All right, so that leads us to the following result. To compute the surface integral of our vector field F over the surface S, then what I'm going to do is integrate this dot product of F with this cross product vector tu cross tv. And this integral here is happening in the UV plane, right? This is an integral over R. In f of r of uv, that's just saying we're evaluating our vector field along the surface S. Here, r is just the vector function that's parameterizing the surface. Okay, so last I just want to note here that when S is an and an explicit surface, so it's of the form z is equal to g of xy, then recall that the cross product vector, tx cross ty, is just minus gx minus gy 1. Okay, so the above here, this expression, this will become what? Well, if the components of the vector field f are p, q, and r, and I dot that with this cross product vector, I'm going to get minus p times gx, and then minus q gy, and then plus r times 1 is just plus r. So that becomes the integrand. And again, I'm going to be integrating in the UV plane. All right. So in the next couple videos, we're gonna illustrate how to compute these kinds of things. And so let's get to it. Thanks so much.